today I'm going to be talking about enclosed area, or area between two curves. And so, up to this point, we've taken some integrals, and so I would expect that we would know how to find this area that I'm kind of shading here in gray. Right? This area is given by the integral of f of x from a to b. That should be pretty familiar. But what if I just introduced a second curve, g of x, and I was interested in the area between them? And maybe I'll call this region R. Okay, so I'm interested in the area of region R. I could probably find the area of region R by taking that integral that I was talking about a second ago and subtracting this area. And this area is going to be given by the integral of g. Okay. So if I'm interested in this area, I could find that by integrating f of x and subtracting the area under g. Okay, but oftentimes, if both f and g are polynomials, it could be easier to integrate if they have, some terms of the same power to actually combine these integrals using one of our integral properties and saying that this is the integral from a to b of f of x minus g of x dx. Okay. And where this all comes back from is, it all comes back to the Riemann sum. And, I'm going to talk about area today. I'm also going to talk about arc length today. Now, that'll be in a separate video. But it all goes back to the area of the idea of the adding up of the area of a bunch of rectangles. Next time when we do volume, it will go back to a Riemann sum. We'll be Riemann summing a bunch of, really small pieces of volume. And so for now, what we're really adding up is, I didn't draw that very accurately. Maybe that'll be maybe we'll do the right Riemann sum. And so the height of this rectangle is given by f minus g, right? That's the difference in their y values. And the width is given by delta x. And so we've got, we've got the sum of a bunch of f minus g's times delta x, which, comes back to this integral from a to b of f of x minus g of x dx. So a natural question you might ask is, what happens if one of the curves is below the x-axis, right? Don't we know that counts negative area? We know that it did, especially last time when we were integrating rates that may have been negative that were causing things to decrease. But, okay, it all goes back. And this is a more geometry-focused idea. We're going to take these regions and we're going to eventually rotate them around an axis or build on top of them or look at the perimeters. So, it's very geometric. And in that sense, we're going to be interested in just the value of the area, like the positive value of the area. So, going back to the Riemann sum, it's going to be the sum of a bunch of rectangles, delta x by f minus g. But down here, g is negative. So when we take top minus bottom, which we're going to be doing repeatedly, top minus bottom, top minus bottom, top minus bottom, always top minus bottom, unless it's right minus left, but we'll get there in a little bit. And if we're going to add up, f minus g is going to be positive because g is negative and we're subtracting a negative. And so again, it'll be the sum of these f of x minus g of x's multiplied by the delta x, length times height, length times height, length times height. Keep adding it up. And then as the number of rectangles goes towards infinity and the width of those rectangles goes towards 0, this will turn into an integral, between a and b of f of x minus g of x dx. Okay, for example, find the area enclosed by y equals x squared plus 2, y equals negative x equals 0, and x equals 1. Okay, so the first thing you want to do, just like you were in geometry class, you're going to want to draw a picture of this. Okay, we know how to draw x squared plus 2. It's a parabola that starts at 2. So it, kind of looks like that. y equals negative x. That's a line that goes through the origin and has slope -1. X equals 0 is the y-axis. Okay, so, all right, I'm just thinking about it there. And x equals 1. Okay, so I'll go up here. That's a vertical line. Let's get that through here. And so when they say the area enclosed by all 4 of these equations, we're looking for a region that is bordered by all 4 of these curves. Okay, so we have y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So we're looking for the area of this region. And maybe you can see what to do on this, but in the future, maybe it becomes less apparent. And you say, okay, well, I'm going to draw a representative rectangle. And this will be really important when we go to do volume. Representative rectangle, not that important today, much more important later. Okay, what's the height of the rectangle? The height of the rectangle is x squared plus 2 minus negative x. Okay, so we're going to be integrating length times height. Okay, the height is x squared plus 2 minus negative x. And the width is delta x. Becomes dx. And we're integrating from x equals 0 to x equals 1. Okay, so I'm going to need to rewrite this, make it a little easier. And then we know what to do from there. So I'm going to freeze the screen for y'all in class. And if you're watching at home, you can just follow along with my steps. But see, just make sure we're taking this integral right. And here we've got the region defined by a couple of inequalities. And as far as the College Board, the AP materials, you don't oftentimes see it defined like this. But I do like these because, in Algebra 1, Algebra 2, we looked at regions defined by inequalities, and we would, graph a curve and shade above, below, depending on whatever. And so we've got these inequalities. X is between 1 and e. Y is between 1 over x and 4. We want to find the area of R. So what I'm going to do is I'm going to help you by drawing a picture, and then I'm going to have y'all find the area. Okay, so 1 to e. I've already labeled 1 and e on the x-axis, and we know that these are vertical lines. This x equals 1, x equals e. Using the wrong color. Okay, so we know it to be between those two things. And y is between 1 over x and 4. What? I know what the graph 1 over x looks like. It comes from above, it kind of swoops down, and then it gets smaller and smaller, dividing by a larger and larger number. It goes towards 0. But y has got to be greater than 1 over x. Okay, so that's kind of like the lower bound of our region. And then the upper bound is going to be y equals 4, which is a horizontal line. It's the set of all points where y is equal to 4. Okay, that doesn't look that horizontal, but you can just imagine. Oh yeah, that looks pretty rough. We're going to be all right. Okay, so R is this region defined by these inequalities. Okay. And so I want y'all to try to find the area of R. If you start with your little representative rectangle and you integrate, and you'll find it. If you're watching at home, you're going to want to pause the video right now because the answer is just going to pop up in like 10 seconds. Okay, so there it is. I set up the integral top minus bottom. Oh, no, that's from 1 to e. Oh, well, wrong color. Oh, goodness. All right. I set it up, I anti-differentiated, I plugged in top and bottom, I subtracted. Okay, we've got a calculator question. And this is, find the area bounded by f of x is 1/6 x to the third minus x, and g of x is e to the x minus 3. Okay, so the first thing is you're going to graph it on your calculator, and it's going to look like this. Okay, just a second, let me bring up the calculator. Okay, so you see here I've got x to the third divided by 6 minus x, and for y1. E to the x minus 3, and for y2, and I'm going to graph this on the standard window. And see, it looks kind of like the figure I drew. Could at least keep it the same with colors. But we need to know where we're going to integrate. Okay, so that's really the main, well, it's not the main thing we're going to use the calculator for, but we're going to calculate the intersection. Okay, so calculate, we know that's where all the good stuff is. Calculate the intersection. That's 5. First curve, second curve, give it a guess. Looks like that's giving us our higher bound that I'm going to call B. That's 0.820473. And we need to keep all of these decimals. I know that you're going to feel annoyed about it. You want to only hold on to 3. I suspect that if you hold on to 5, you should be good, but it's not worth the risk. Because if we early round, it can kind of, the rounding can propagate, and we could be off, by a couple in the last decimal. And that could be the difference between being right and being wrong in the free response section. Okay, then I'm going to find the intersection on the left. So I'm going to calculate the intersection. First curve, second curve are the same. I'm just going to switch up the guess to like -5. So it's just looking more over there. And, okay, A is, can you read me that again? Okay. All right. So we've got our bounds of integration. And so I'm going to set up the integral. This area between the two curves, which I'm shading in green here, it's going to be given by the integral from A to B of f of x minus g of x. F of x is the blue one. It's on top. Okay, right, always top minus bottom, not just f minus g. And now what we're going to do, now for this one, it would probably be faster to just type it in directly. But for a lot of the area volume questions, you get these two values here, and you're going to want them for more than just one part of a question. So what I'm going to do is I'm going to show you what you should do if you need this. What you're going to do is you're going to store -3.36067 using STO into A. And then it says, okay, yes, I know that when you say A, you mean -3.36067. And then I'm going to do the same thing for B. 0.820473. And we're going to store that in as B. All right. And then whenever you press B, it knows that you mean 0.820473. And now I'm going to integrate. I'm going to use Math 9, right? It's a nice integral. And that's from A up to B of, okay, well, it's top minus bottom. Blue minus red was y1 minus y2. So I'm going to go call on y1. Variables, y variables, we're in function mode. We'll go and do polar and parametric in the second semester. y1 minus y2 with respect to x. And then you let it think for a minute. And that's 10.321. And we round at the very end, but not before. All right, so well, what would happen if the curves intersected more than once? That's kind of another thing that can happen. I see that, for a while, F is on top, but then it's on bottom. So there's pretty much two ways that we could deal with this, as far as I'm concerned. I feel like you could find the red area by just, integrating between A and B, top minus bottom, in this case is F minus G. And then we could integrate from B to C, G minus F, because G is on top there. But, you know, especially, oh, whoops. I forgot to label that as the blue area. Okay, but if it's a calculator type thing, it's a lot of typing. And can anybody think of a kind of a shortcut or a faster way to do this? Yes? Yes, use the absolute value from A to C. Because really what we want is we just want the height of our rectangle to always be positive. Okay? That's what we need. And when we switch at B, if we're doing F minus G, then all of a sudden G is bigger than F, and this becomes a negative number. But we could just make it positive by taking the absolute value of the integrand. So, you know, by hand, not very useful because we aren't very skilled at taking an antiderivative of a thing involving an absolute value. In fact, that's not something that we've done in this course thus far. It appears that that's something that we're going to be doing later because I just saw the 2018 practice exam that they give out to us, and there was a thing on the free response where you had to integrate a thing with an absolute value on it. So that's something that we're going to look at. I was just talking to Mr. Messner about that this morning on the phone. Or A to C of the absolute value of f of x minus g of x, or the absolute value of g of x minus f of x from A to C. Doesn't really matter. Okay, but those are your options. All right, and here we've got another kind of type of problem. Okay, you've got this region bounded by these curves, and then they're going to ask you to find the x value that would split this area into two subregions of equal area. Okay. So, and they'll say, like, find the value of k for which the vertical line x equals k splits this region into two subregions of equal area. Okay, so what we need to do is, there's a couple of ways to do it. If you already know the total area, you could set the integral from 0 to k equal to half of that. But we don't really know what that is at this point, so I think there's probably a better way. I think what we're going to do is we're going to set up from 0 to k, and that's going to need to equal the area from k to 2. Right? 0 to k, and then k to 2. And they need to be equal. Okay, so, and again, we're integrating top minus bottom. Okay, draw yourself a little representative rectangle. Okay, top is e to the x. Bottom is negative 1. And then the integral from k to 2 is going to be, again, top minus bottom, still the same, e to the x minus negative 1. Okay, and then I'm going to rewrite it. 0 to k of e to the x plus 1 equaling the integral from k to 2 of e to the x plus 1. Okay, I'm going to anti-differentiate. Antiderivative for e to the x is what? Yeah, e to the x. E to the x is its own derivative, so it's going to be its own antiderivative as well. Plus antiderivative for 1 is just going to be x, 0 to k. And that's going to be equal to, well, it's going to have the same antiderivative from k up to 2. And so I'm going to actually kind of go down there. And I'll plug in k, plug in 0, and then I'll, over here, plug in 2. Wait, that's not 1, that's x. E to the 2 plus 2 minus e to the k plus k. All right, so now I've got an equation in k that's looking like it's something that maybe I could solve. Maybe I'm going to need the assistance of technology, but I'm going to be able to find this because I'm just down to one variable. Okay, so I'm going to first kind of like add across that e to the k plus k. And so I'll have 2 e to the k's and 2 k's. And then I'll deal with this thing. I'll have minus 1 is equal to e to the 2 plus 2. So I'm going to subtract e to the 2, and I'm going to subtract 2. Set it equal to 0, because this is the type of thing. If I've got just e to the k, I could solve that using logs. Since I've got e to the k plus 2k, that's not something we're going to be able to solve by hand. We are certainly going to need to use technology. So I'm going to take this equation here, and I'm going to solve it using technology. Okay, here's our technology. We're going to go back into y equals. We're going to plug in, I'm going to get rid of that just so we're not anything. 2e to the k plus 2k minus, I'll do the minus 1 and the minus 2 together, minus 3 minus e to the 2. And I'm interested in where this is equaling 0, and specifically I'm interested in where this is happening between 0 and 2. So I'm going to set the window to 0 to 2, just so I'm not seeing anything. Now I doubt there's going to be more than 1 0 to this thing, but I'm going to look and find something. Just only be there it is. Okay, so that's going to be my value of k. I need to find that 0, so I'm going to calculate the 0. It's to the right of this. It's to the left of that, and if I was smarter, I would have just typed in a right bound of 2. Yeah, but I wasn't thinking clearly. And then, so I'm going to go here, and that is 1.347. Okay, so this is 1.347. And I think this is all I got for you in this video. I might come back with another video on integrating with respect to y, adding vertically, or some more tricky problems. But for now, this will be it.